If our forecasting horizon is medium or long term, then likely we're going to look at a trend forecasting method. So we're looking at the patterns over time. We're going to fit a pattern to the data, and then we can use that pattern and the formula that we get with it to forecast forward. So a linear trend is we're looking for a pattern in the data, and our linear trend could be upward sloping, for example, or downward sloping. We also have trends that are more polynomial in shape, and polynomials can be of different degrees. So a polynomial of degree 2 looks like this. A polynomial of degree 3 looks like that. A polynomial of degree 4 has another turn. So you might have a polynomial shape that you find in your data. Does it go up and then down? It's a polynomial of degree 2. If it goes up, then down, then up again, it's a polynomial of degree 3. Now, of course, these can also go the other direction as well, just like the linear trend can go the other direction. So polynomials are really about the number of turns. How many different directions does your curve go? You may have a pattern in your data that is a growth curve. So growth curves look like that. You might have a logarithmic shape. You might have an exponential shape. Okay. So the key is to plot out your data and identify what kind of trend you have. So in Excel, you can fit a model to your data that represents one of these patterns, one of these trends. And when you do so, what it will create for you is it will create the formula for that trend line. You can then use that to forecast forward. So there's another video on Blackboard where you can see how to do that in Excel. And here I'll show you just some of the hand calculations you do after you get that information from Excel. Before we leave this slide, notice there's a third type of trend forecasting. It's called trend adjusted exponential smoothing or double exponential smoothing. We're not going to go into that in this course. You can read more about it in the textbook if you're interested, but it's beyond the scope of this class. So let's look at our complaint data. And let's suppose that we take the first 7 years worth of data and we plot it in Excel. So you'll notice here that on the horizontal we have time. Oh, sorry, I take that back. We're going to plot not the first 7 periods, but we're just going to do the last. So if we plot periods 8 through 15, that's what you're seeing here. So there's our time on the horizontal, and on the vertical we have the number of complaints at our bank branch. So in Excel, we have fitted a linear trend line to this, and we have asked Excel to give us the formula. So here we have the formula, and please see the other video on using Excel for how to get that. Once you get this formula, you can then use it to forecast the number of complaints in period 16. So our forecast for period 16 is going to be equal to, and this is where we take that formula, negative 2.881, and then that x, that's where your time number is going to go. So that's where 16 is going to go, plus our 100.38. So this x is a placeholder for our time measurement. And if we're forecasting for period 16, then we're going to place in 16 for that x. If we're forecasting for period 17, we're going to put 17 in for that x. So to forecast for period 16, it's negative 2.881 times 16 plus 100.38, which gives us 54.28. If you want to forecast for period 17, it's negative 2.881 times 17 plus 100.38, and that gives you 51.4. So you'll notice that if we were to add these points onto our graph, is continuing this downward linear trend that we identified. Now, what if, instead of just using the last numbers, the 8 through 15, what if we use the entire data set? Periods 1 through 15. Well, in the other video in Excel, we took periods 1 through 15 and we fit a pattern to it. And you'll notice this curve here. This curve is a polynomial. Okay, and you could choose to have polynomials of degree 5, degree 7, but notice that when you have a polynomial, switch colors here, a polynomial of degree 2, that's going to have an x squared in your formula. So you're going to have to square one of your time periods. If it's a degree 3, it's going to have an x3 in your formula. If it's going to be a polynomial of degree 4, it's going to have an x4 in it. So while the accuracy of your forecast and the ability it has to fit your data might get even better, polynomials of degree 4, 5, 6 become a lot more complicated to calculate. We have Excel for that, so that's not too bad. But it also is much harder to explain. Explain why in the first couple years it goes down, then it goes up, then it goes down, then it goes up. Remember, you have to explain to your stakeholders what the forecast is telling you and why it's telling you what that is. So if you're getting too many polynomial degrees, the formula gets too complicated and really you can't explain what it's telling your stakeholders. So for example, let's say we fit a polynomial of degree 4. Okay, if we fit a polynomial of degree 4 in Excel, we get our forecast for period t is equal to 0.0204 t to the 4th minus 0.649 t to the 3rd plus 6.4066 t squared minus 19,891 t plus 7637. All right, tell me about the complaints at your bank based on that formula. What is it telling you? Well, that formula, super complicated, fits the data very nicely, but what does it actually mean? And so it can be very hard to explain to your customer base. We could use that formula though, and we could find the forecast for 16 and the forecast for 17. And if you were to use this polynomial, the way that it would work is you would take 0.0204, and if it's the forecast for period 16, it's 16 to the 4th, minus 0.649, 16 to the 3rd, plus 6.4066, 16 squared, minus 19.891 times 16, plus 7637. Okay, and you throw that all into a calculator and you get 7638. Okay, so that's what you're seeing here with that little star. So note that based on this forecast, the next forecasted year would have an increase in complaints. Well, now let's calculate the forecast for period 17 based on these numbers. Okay, so exact same formula, but this time we're replacing 17 everywhere you see a T, or if you're looking at the Excel formula, everywhere you see an X. Well, if you number crunch this, you find out that the forecast is now 105.02. So essentially we're saying that the number of complaints is going to skyrocket. Well, you have to ask yourself whether this makes sense. So just because the pattern that you found fit very nicely with periods 1 through 15, does the forecast that it's giving you for the future make sense? Because it's essentially saying that the complaints are going to go up drastically. Is there anything that's happening at the bank to make you think that this is actually what would happen, that this might be true? If not, then you need to ask yourself whether or not this is a really good model for forecasting forward. Perhaps you need to choose a more simple pattern, maybe not a polynomial degree 4, maybe a polynomial of degree 2, or a linear trend. When you are doing your trend forecasting, you have to take into consideration seasonality. So we talked a little bit before about ice cream and how ice cream sells more in the summer and less in the winter. So we have this seasonal variation. Well, notice that if we took out the seasonal variation, we could identify a trend. Okay, so it looks like in 2003, 2004, there was a peak in sales, and since then it's lowered and kind of flattened out a bit. Well, if you have seasonality in your forecast, you want to remove the seasonality, identify the trend, project forward, so get the formula for your curve, use that to forecast forward, and then add back that seasonal variation. Now, how you do that process is beyond the scope of this class. You can read more about it in the textbook. Now, some other examples of industries that would experience seasonality. Well, we see seasonality in retail, right? We buy more at certain times of the year, like Christmas. We see more in terms of seasonality in terms of utilities, like residential gas. So we heat our houses more in one time of the year versus the other. We see this in retail, besides just Christmas being increased sales, but you can also see this variability within a day. So, for example, people buy more like clothing, more household goods, electronics, things like that, around payday. So there's a cycle within the month or within every couple weeks. In banks, there's more traffic at noon and at closing time. So these are seasonal variations as well that we might have to take into consideration depending on what our company makes. So we take out the seasonal variation, we find the trend, we forecast forward, and then we figure out where we should be in terms of the seasonality and adjust above or below the trend based on that. And that's called re-seasonalizing. So we de-seasonalize and then we re-seasonalize.